Hello class, in the name of God, we continue the rest of this section. In last section we explained about genetic algorithm. Uh, Genetic algorithm is the most popular version of EA algorithm that developed since 1970, and then it is developed by Holland and some other scientists. The first version of GA is simple GA, and we explained that the representation of simple GA is binary, recombination is endpoint or uniform or one point, mutation is bit flipping, parent selection based on fitness proportionate or EWS. Survivor selection is based on age of all children replace parents. Especially the main emphasis of this version is emphasis on crossover. We explain about the simple GA and some version of crossover and mutation, such as one point crossover and uh, roulette wheel selection. It is based of random and fitness, and also an example that find the maximum randomly. And in a previous section we explained about some crossover operators such as endpoint and uniform crossover that this version don't have a bias. And we explain about that the mutation produce the genetic material, but crossover don't produce genetic material. It only exchange the location of gene. And we explained about this fact that we have some representation, such as binary representation. Each gene is 0 or 1. Integer, that each gene is integer value, real value, and permutation. Permutation is a special version of the representation that each gene is integer, but uh, each value exists in a list one time, not more, not lower, and it is not repeat, such as some problems such as 8 queen and Napstack and other problems. We explain since this page in previous section, and in this page a Greek code representation is introduced. It is a binary. It's an special binary representation, but with gray code. Gray code is a binary code that each small change in bits cause a small change in a value. For example, in binary, this behavior is not exist. For example, and it is for example 0, a small change, for example 1 bit change to uh, 0 change to 1, it is 0 value, but it is 8 value. A small change cause large change in and in a phenotype. In some version, it is not a good change, the undesirable. It is undesirable that a small change cause a large change in a phenotype. So they use gray code representation that a small change cause a small change in gene cause a small change in phenotype. It's not important for you, and in today nowadays it is generally accepted that it is better to encode to integer or floating or real value problem, and the binary representation sometimes is not used nowadays. We explained about the representation. We explained about the integer representation in this page. Integer representation is a representation that each individual or each chromosome or each solution of problem includes some gene, and this gene value is integer. For example, 7, 10, 20, 0, 13, and other values of integer. Some problem is integer, and it is better to use uniform crossover or endpoint crossover, and it is better to use bit flipping mutation that change the location of 2 bits. Also, there are some other mutation. For example, you can change a small change, for example 7 to 8 or to 6, and it is a mutation. And some problem is real value, because the problem have a real value solution, such as Ackley function. And this is an Ackley function that it is have a full of local mean. It is all of this minimum are local mean, but the aim of the problem to find the global mean, the lowest value of this function is a location that this function have a has better the lowest value. It is a Ackley function that used for test some easy problem. Sometimes easy algorithm can find, for example, this value as a minimum. So it is acceptable, but it is not the best solution. The best solution is here, and it is used for a test of some algorithm of evolutionary. In this page, an extra explanation exists that say mapping real value to bit string value. It is used for some real value that with integer or bit string binary value, such as GA. GA is a algorithm that can solve the problem only by integer or binary representation. So we can't use GA for some real value problem. In this page, it is shown that it is possible to map real value into integer value and use, for example, GA for solve real values problem. It is not acceptable nowadays to use this method because there are many real value EA algorithm, and this change is not desirable and it's not uh, acceptable for change the representation and use, for example, GA to solve the real value. Directly, it is better to use a real value EA solution such as ES, evolutionary strategy, that we explain it in some next section. And floating or real value mutation. And in a floating or real value mutation, each bit of a chromosome is a real or floating. For example, it is 2.5, or it is 7.07. Each value is a floating or real. The mutation is an operation that change that cause a small change. For example, we change 2.5 into 2 and, for example, 6. It is a small change, and we use uniform mutation. Uniform mutation is a uniform value from lower bound to upper bound. For example, from negative of this to positive of this, and we produce a random value, and it's added to the each gene if the mutation occurred. Or it is another solution to use mutation to substitute two value of gene instead of change of each gene. It is a floating point mutation. Also, we can use other distributions such as Gaussian or normal distribution. It is a normal distribution with average of 0, and the sigma is the standard deviation of floating of normal or Gaussian distribution. In this way, each time a value is produced randomly, and this value added to the gene, each gene, for mutation. So the real value mutation or floating point mutation is a small change to each gene. Crossover operation for real value. If we have two parents, for example, that each gene of a parent is a real or floating point, we can have two types of crossover. One is the same as integer representation. The change of, for example, x and y. It is we can change. It is a discrete crossover for real value. It is the same as integer representation or binary representation. But we have a new version of crossover that is named as an intermediate. Intermediate is a way that we can produce the gene of children by this formula. Some percentage of one parent and some percentage of other parent are mixed together, and the Z, or the value of gene of children, is produced. So in the discrete value, the gene of each offspring or children is from first parent or second parent. It is here. But in intermediate method, the gene of each children is a mix of both of first and second parent. Alpha is a value that share the percentage of each parent. If alpha is equal to half, it share both of the value equally. For example, here alpha is half, and in this, it is the first parent, it is the second parent, it is the first children, it is the second children, and it caused half multiplication by first add by یک minus half, it is half multiplication by the second parent. Both of this value is equal because it is half and it is half. For example, if we select it is 2, it is 0.2, it is 0.8 for first children. For the second, reverse, 0.8 and 0.2. And it is an intermediate crossover. So you can see that this method produced new value, such as so its behavior is the same as mutation. It don't change the location of the gene. It produces a new value for the gene. So it is true that we say that intermediate representation have behavior such as mutation, and it can produce genetic material, new genetic material, because it don't change this location. It mix the value and produce new genetic material. So it is a new behavior for crossover of real value. Intermediate crossover. So intermediate crossover produce genetic material. In this section, we have an example that we select this part and this part of the first and the second parent, and we use this formula with alpha equal to half, and it produces this type for the first children and second children. And the first part is the same, but the second is a mixed. Here all of the gene mixed together by this formula or intermediate crossover, and Uh, this the disadvantage of this problem is that both of the gene is equal because it is half. If we use, for example, 0.2, the first one is 2 and the second one is 8. For the first and for the second it is 0.8 and it is 0.2 for the second children. But when we use the alpha equal to half, both of them is half, and the value of first and second children are equal. Another representation is named as a permutation representation. Permutation representation is an special representation that each gene is an integer value, but each of this gene occurs exactly once, not more, not less. Such as some problem, such as sort problem. Sort. You have some digit, and you want to sort this digit. It is have a permutation representation, because each time you sort this value, you, for example, you have all of these 6 points without any repetition or delete. All of the value must exist exactly once. It is named as a permutation representation. Another problem that use this representation is 8 queen problem that we explained it in previous section, and also TSP, traveling salesman problem. Traveling salesman problem is a classic problem, or postman problem. For example, postman should send mail to this location, for example 1, 2, 3, the last is 30. The best route and the best following of this value is the way that it can send the mails to the distance with minimum, to the destination with a minimum distance. For example, if he can start from here, then here, then here, then here, then go to the here, then go here, it is so the chromosome is 14, 15. It is the order of the destination, and etc. If it start, for example, from here, the chromosome is 3 to 7, and it is 8, 9. The best chromosome or the best solution is the route with minimum distance. You have, for example, a distance between these 2 points, between these 2 points, between this, and the best solution is the solution that the postman or the salesman can go with the minimum distance value. It is another, for example. All of the destination or all of this number exist in the list or in the solution exactly once. It is a certain location, so the certifactorial combination of solution exists. It is very large solution, a space solution, and the aim of EA algorithm is to find the best order of this location that produce the minimum value of destination or summation of distance between this location, for example. It is another form of permutation problem. The mutation for the permutation problem, as we explained it in previous section, it can be a bitwise or select 2 bits and change the location of this 2 bit. It is a bitwise or substitution. So we need to mass change at least 2 value, because if we change only 1 value, the rule it may produce illegal value, because each value must exist exactly once, not more, not less. So we should change the location of 2 bits. In this part we want to explain about some version of mutation for permutation representation. The first version is insert mutation. In this method, as it is say here, pick 2 allele or 2 value at random. For example, if we select 2 and 5, move the second to follow the first, and insert, or we insert 5 after 2 and change here. The value is here. Another bit is not changed. Another bit such as 1, 3. In this method, the order is preserved, and also the agency is preserved. It change only a small change. It causes only a small change in the solution, and it is named as insert. We select 2 bits randomly and insert the second in after the first. It is named as an insert. The second one is swap mutation. This version, we select 2 gene randomly and swap this location. We change the location of first and second. This version preserves the agency, but it can preserve the order, some order change. The third version is inversion mutations. In this method, we select two location randomly and invert these two and all of the values between these two values. These values reverse. So 2, 3, 4, 5. It is 5, 4, 3, 2. It is a reverse of this part. This version also preserves the adjacency and disrupt the order. And the last version is scramble. We select 2 bits or 2 gene and scramble, randomly arrange the values between these two bits or these two allele. We change the value of this location randomly. As you see here, this version has a most explore than third version. Third version has more explore than second version, and the second has more explore than first version. The first version has the more exploit. It has the most exploit and the least explore, and reversely this last have a more explore and the least exploit, because this solution is differ from this solution or individual. Crossover for permutation. And in this shape we have 5 gene with permutation representation. So 1 point crossover cause illegal solution because we have repeated value in gene, or some values are missed, such as 4 and 5. Here we have 2 repeat gene and we don't have some gene values such as 1 and 2. It is not acceptable for the permutation to repeat some values and miss other values. We want to explain about the crossover version for permutation. The first one is order 1 crossover. As it is explained here, this method, the aim of this method is to preserve a relative order the elements. The explanation of this method is choose an arbitrary part from the first parent, copy this parent to the first child, copy the numbers that are not in the first part to the first children. And we explain with an example here. We have 2 parents, first parent and second parent. Firstly, we select 2 bits randomly, for example, this part and also this part is the same of the location. For the first children, this location is copied exactly to the same location. It is from first parents, but we fill the other locations from other parents, and we have 5, 4, 5, 6, and 7. It is from the first parent. It is from the first parent, but we continue to fill the last location, the empty location, such as here. We start from here, from the next parent. So if it is exist in this part, we don't repeat, and we go to the next value. It is 1. It's not here, so it's right here. Then it is 4. 4 exists here, so we jump to the first. It is 9, so we don't have 9. It is here, we don't have 9, so it is 9. Go to the first and continue. It is 3, we don't have 3, so fill it. It is 7, we have 7 here, so jump to the next. We have 8, we don't have 8, so fill it with 8, and it is 2, we don't have 2, so it is here. It is exactly this, and it is 1. It is named as a order 1 crossover for permutation representation. So you can see that this individual, or this solution, is a other arrangement of 1 to 9. It is another arrangement. It is another arrangement. It is 2 parents that produce children by this method. Order 1 crossover. We explain about some other version of permutation representation in next section.